So we've seen how to use the impulse momentum theorem in some simple settings. Specifically, we worked out a simple case of pushing a block along the track or floor, and we also worked out a situation where a baseball collided with a baseball bat. Two of the main uses for momentum is to understand explosions like dynamite or decaying nuclei or things like that, and inelastic collisions. So I have to get jumping a little bit ahead of myself. You know, I had a choice when laying these out, and I thought about doing energy first and then momentum. But that requires us to understand a little bit more math, and we have to understand about dot products first. So I chose momentum first because it's pretty easy. Also, most people understand impulse momentum pretty intuitively. But that means we're kind of not going to talk about the simplest possible collision, though. Unfortunately, impulse is only enough to guarantee that you can solve it if the collision is between two things which stick together. So you can think about two balls of silly putty that collide, or I don't know, a car and a semi-truck that crumple up together. Those would be situations that you can describe using momentum conservation alone. For other kinds of collisions, namely when things bounce off each other, or even more complicated is where they bounce off each other, but they're a little bit sticky. For those, you really need other ideas. For the ones which are perfectly elastic, those are the ones that really just ricochet off each other with no stickiness. Those you need to use, energy conservation ideas. So we're going to limit ourselves to this case. Inelastic collisions, that's when things perfectly stick together. So two cars stick together and kind of crumple up as one big ball, or two balls of Play-Doh collide, or something like that. Very good. All right. So I'm going to go through, and what you're going to see is the logic for how to handle these is very similar. In some sense, to some degree, an explosion is just a collision running backwards. So if you had an inelastic collision and you put it in rewind, it would look like an explosion. So it's really the same analysis in both cases. All right, let's go through something really simple. Let's imagine that we have two figure skaters, and they don't like each other. Okay, so they don't like each other, and they push on each other, and they're sliding on ice. I just keep saying ice in some of these examples so that I can ignore friction. It's not that you can't handle it. It's another force. You could calculate its effects. You could find the impulse it produces. Turns out for these interactions, which are very quick, friction tends to be not very important because the average value of friction is usually not that large. And if you are integrating it over a small time interval, it's going to produce a small impulse. So it's not as significant as some of these other forces. So in this situation, these two ice skaters don't like each other. They both push off and they start sliding. In fact, this skater is going to say, oh, I felt a force, and so I moved to the right. Whereas the other person, using Newton's third law, is going to say, no, I felt a force and I went to, I go the other way. They both move. So there's a recoil effect. So that's fine. We can use impulse and momentum concepts to solve for what happens. So let's imagine that this person is labeled with a 1, and this person is labeled with a 2. And I'm going to go ahead and say that the mass of person 1 is 70 kilograms, and the mass of person 2 is 80 kilograms. And we're going to assume that initially they were at rest. They were just stationary, not moving anywhere. So the initial velocity for 1 equals the initial velocity for 2 equals 0. And then let's say, finally, after it's all said and done, that person 2 had a velocity, so V2 final is going to equal, you have to be careful with your labels here. Let's be consistent. I should say V1 initial and V2 initial. V2 final equals, let's say it's 3 meters per second. Okay. And our task is to find the final velocity of person 1. What are we expecting? Well, this person on the right gains momentum, right? They started at rest, no momentum, and they gained positive momentum, okay? Person 2 was pushed to the left. I expect the final velocity to be negative. Let's see how we can work this out using momentum concepts. And I want you to notice, I have not specified the details of how they actually pushed on each other. All we know is how they started and how they finished, and that's going to be enough. When you can use conservation laws, that's how it works. You just need to know what happened, what was there at the beginning and at the end, and oftentimes, especially for these explosion and collision problems, the stuff that happens in the middle, not your problem. You don't have to worry about it. Okay, so person 1 pushes on 2, 2 pushes on 1. Now I'm going to use the concepts. As always, what's the first thing I have to do? I have to choose a system. Now, we get a choice. We can make the system be person 1. We can make the system be person 2. Or we can make the system be 1 and 2 in total. If I were to make the system be person 1, because you might say, oh, I want to find 1's final velocity. There's a logic there. Does it kind of make sense? The problem is, then you would need to evaluate the impulse on person 1. I don't have any knowledge of the details of how they pushed or how long they pushed, anything like that. And the same kind of thought and analysis would apply to person 2. Instead, in fact, almost always, if you can, it's helpful if you kind of mentally draw a bubble around a group or configuration for which the outside world doesn't influence them. So if I make 1 and 2 my system, I see that there are no outside forces. That means there is no impulse coming from the outside world. That means J equals 0. So I'm going to make my system be 1 and 2. It's a little unusual, 2 different objects, but I'm going to make the whole system be both of them. That allows me to state, first off, I have the change in momentum. What does that mean? Well, it would be the momentum of 1 plus the momentum of 2. That would be the total momentum in the system. That equals the impulse on 1 and 2 as a whole. So this force in between them, that's kind of their own business. But that has nothing to do with the rest of the world acting on them. So if I think of them as a pair, you can ignore this complicated interaction that you don't know about. So if I make this my system, the impulse is simply 0. So what I learned is that the change in momentum of 1 and 2 total equals 0. So that says delta P1 plus delta P2 equals 0. Should have had an arrow up there. Apologize. Therefore, the change in momentum for person 1 equals minus the change in momentum for person 2. And I can simply plug in my formulas. This says that mass 1 times velocity 1 final minus velocity 1 initial equals minus mass 2 times velocity 2 final minus velocity 2 initial, like that. The initial velocities for both of them were 0. And I find the following expression, that the final velocity for skater 1 equals minus m2 divided by m1 times v2 final. Plugging in my numbers, I have that v1 final equals minus, let's remember, 80 divided by 70 times 3. And the units will come out in meters per second. So that's going to be 24 divided by 7. So that's 3.4 or something like that. Call it 3.4-ish meters per second. Okay. So that's how you can choose the system in a clever way to make your life simple. So I reiterate, I found a way to make a system where there was no outside force acting on it, so the impulse was 0, meaning the momentum would be constant or conserved. So if there's no impulse, we say that the momentum is conserved, meaning that the initial momentum equals the final momentum, or another way to say it is the sum of all the changes in momentum must be 0. That's a good way to solve it. That's an explosion problem. That's all there is to it. So if you take a stick of dynamite and it breaks into 3 pieces, each with their own masses and velocities, it's the same exact problem. Just change the drawing. So you would add up, in that case, all of the momenta before, and add up all the momenta afterwards, write that down as an equation, and solve for the thing you want to learn. Okay, so explosion problems are always that way. Let's talk about a collision problem. Let's talk about an inelastic collision. So that means 2 cars or 2 objects come together and they stick together and they move. Afterwards, they move as one thing. So let's imagine that there's a semi-truck and there's a pedestrian. I don't know. Maybe that's a little grim. Let's just imagine I have 2 objects that start separated and then come together. So I imagine I have a ball, let's say it has mass 1 kilogram, and initially, I'll call this object, I'll say that this has an initial velocity, so v1 initial, and I'll say the initial velocity is 10 meters per second. And then it's going to collide with another ball of mass 0.5 kilograms, and I'm going to say that v2 initial equals 3 meters per second. what I would like to know is after they collide, this is before, after we assume it's just one giant blob of mass 1.5. So the total mass would be 1.5 kilograms. And I would like to know what is the final, so V final, and you could say V final of the 1 kilogram mass, or you could say final velocity of the 0.5 kilogram mass, or you could say the final velocity of the pair because they stick together and so they have the same final velocity. After, I apologize. Okay, so how will we do this? Again, like in the last example, it is very nice if we can choose our system so that there's no force acting on it from the outside. So if there's no force, so I could either make the system be the 1 kilogram mass, but that's not going to work because that mass does feel a force. You can make the system be the 0.5 kilogram mass, but that system feels a force. Instead, you can make the system be the total, the pair of them, and from the outside, that system does not feel a force. So let's do that. So make the system be, so step 1, choose the system. So that'll be the 1 kilogram mass and the 0.5 kilogram mass. And if I do that, so mentally I'm kind of imagining a bubble wrapping around the pair of them, separating them from the rest of the universe, then I expect the momentum before for the pair to add up to the momentum afterwards for the pair. So that would tell me that the momentum before would be mass, so it'd be, it would be the 1 kilogram mass times its velocity, 10 meters per second, plus 0.5 kilograms times 3 meters per second. That must equal the total mass of the final state, which is, well, that's just 1.5 kilograms times the final velocity. And we learned then that the final velocity equals, I have to do this as 10 plus 1.5, so that's 11.5 divided by 1.5, and the units on that will be meters per second. I can use my calculator here, use my phone. Oh dear, come on. So I have 11.5 divided by 1.5, and I get 7.66666. That kind of makes sense. Think about what we have here. We have a larger mass moving pretty fast, overtaking a smaller mass, and they collide and stick together. Well, you know, if you were the smaller mass and something larger, well, really wouldn't even have to be larger, but something ran into you from the backside and you kind of got stuck to it and carried along with it, your velocity is going to increase. On the other hand, if you're the larger object running into something that's smaller, you end up slowing down at least a little bit. Okay, so that makes sense. The larger mass slows down in that case, and the smaller mass in front speeds up. Let's do another example. Let's do an example in 2 dimensions. Let's imagine that there is an intersection And let's imagine that there is a car traveling at 10 meters per second. So the initial, label this car 1. And over here, I'm going to have car 2. So I'm going to say that V initial for car 1, so car 1 initial, equals 10 meters per second to the right. So that would be x hat. Whereas for car 2, let's say that car 2 has, let's say it also has a speed of 10 meters per second, and that would be in the negative y hat direction. Okay, so it would be a negative velocity in the y direction. And we're going to assume that they collide and stick together. Well, okay, I chose the numbers to be symmetric, so you know the answer pretty much has to be that they end up kind of going on a 45-degree line. So what I want you to imagine is they collide, they crumple up together, and let's predict where they end up. Let's predict the final kind of path after the collision, or the final velocity right after the collision. So just a comment, in these sort of collision problems, we're ignoring friction. We're ignoring any force that takes a long time to develop. We only are, because the change in the motion is concentrated at the moment of the collision. And that means we really only have to consider the forces present at that moment. Okay, so here's what we're going to do. I want to find the velocity of the cars as they stick together and slide. And then I also would like to find the force, the average force, sorry, acting on car 1. So during the collision. So to do that, I'm going to actually give you a timetable for the collision. Let's say delta t for the collision is probably like half a second. I have no idea, but let's just assume that the collision takes place over half a second. And so we want V final of the pair, and I want to know what is the average force on car 1 during the collision. Those are the things I would like to have. Okay, is everyone clear? I'm going to erase the picture so I have more room. All right, as before, since at the beginning I don't know about forces, I'm going to make the system be the pair of them. And that allows me to get around any missing information. So I want to make the system be, or the system is 1 and 2. That tells me that there's no impulse on that combined system, so the momentum of that combined system must be constant. That means that the momentum of 1 initial plus the momentum of 2 initial equals momentum total final after they crumple up together. And then I just have to write these down in equation form. So let's do that. The momentum of 1 at the beginning is going to be, I should have told you that. These are identical masses. Let's say they each have a mass of 1,000 kilograms. Choose nice round numbers. So this tells me they both have the same mass. They're identical cars. This tells me that the mass of 1 times the velocity of 1 initial plus the mass of 2 times the velocity of 2 initial would equal the final total momentum. I plug in what I know. This is 1,000 kilograms times, it's the same factor of 1,000 for both, so I'm going to pull that out. And I have 10 meters per second x hat minus 10 meters per second y hat And I rearrange it, and I find that the total momentum final for the pair is equal to 10,000 times the vector x hat minus y hat. Now, if you think about that, that vector lies along the 45-degree line into quadrant 4. It would have a magnitude then, if I would work out the magnitude, it would be 14,400, something like that. So the magnitude, okay, anyways, that's what it would be. If I wanted to find the final velocity of the pair together, that's just going to be the total momentum, final, divided by the mass total. Remember that it's one object now. So to find its velocity, you divide by the total mass. That's simply going to be 10,000 divided by 2,000. So that's going to be 5 meters per second, x hat minus y hat. Or if I'm working with magnitudes, this is going to be 1.4 times 5. So let's call it 15. It's going to be 7. So the magnitude of V final is going to be about 7 meters per second. Okay, so they each end up, so they both were traveling. They were both initially traveling at 10 meters per second, and at the end they're traveling, sliding at 5 meters per second. Now, in real life, they don't travel at that same speed forever. Friction, if you wait long enough, if things slide, the effects of friction accumulate and it'll slow down. But during the collision, you can ignore friction and you focus on that. Okay, we have now the last part of what I wanted was to find the average force on particle 1 or car 1. So to do that, I need to know, I'll have to write down here, the initial and final velocity. So I know now, I can kind of add that to my knowns, that the final velocity for both of them, because they're stuck together, is 5 meters per second times x hat minus y hat. Okay, that's for the final velocity. If I want to find the force on one, then I need to rethink everything. Well, not really everything. I've learned something. That's still true. No matter how I mentally think about the system, that's just the way you define the system is a mental construct. The objects are what they are. So once you identify a kinematic quantity after you're done, yeah, that's all good. So I can use this now for the final velocity of car 1. And I know the initial velocity for car 1. So I can go back and use the impulse momentum theorem for car 1. Now I have all the information about momentum. I can turn it around and solve for the impulse and then solve for the average force. So let's do that. So I would say now for this one, make the system should be car 1 only. And I want to say that the change in momentum for car 1 should equal the impulse on car 1, which should equal the average force times delta t. Reinstating vector labels. So now I just have to write this out. So for car 1, the mass was 1,000 kilograms times final velocity, 5 x hat minus 5 y hat, coming from from here, minus the initial velocity for car 1, which was 10 meters per second, x hat. So that tells me that the change in momentum for car 1 equals 5,000. They're all meters per second. Here, I should have been more careful. Kilogram meters per second times x hat, minus x hat minus y hat. Okay. That is the final momentum of car. That's the change in momentum of car 1. That must equal the impulse on car 1, or turning it around, the average force on car 1 would equal the change in momentum on car 1 divided by the time of the collision. And if I think about that, 5,000, got my numbers there, and then I want to divide by delta t, but delta t is a half, which when I divide by it becomes a factor of 2. So that's going to give me 10,000 newtons, and it points along there you go. So it'd be negative and be x hat plus y hat. If you work out the magnitude of the average force on car 1 is going to be 14,000 whatever plus change newtons. Okay, it's a big force. You don't want to be hit by a car. Okay, so let's recap. That's a long video. I apologize. I'm getting a little exhausted here. I've been at it all day. This is kind of the full range of what you'd have to do with just momentum alone. So for more complicated problems, you actually take the same general scenario, and to answer one question, you might group it one way, and answer another part, you might cut it in a different way. So to identify the final velocity of this total pair of things, we made the system be both of them, 1 and 2, and that way there's no impulse from the outside. However, if the question asks you to find a force, you're going to have an impulse. If you don't have if you don't have an impulse anywhere in the problem, it's like you don't even see that the forces are there. So if you're trying to solve for a force, you need to write the system or choose the system so that there's an impulse, and you want it to be the impulse pertaining to the force you're interested in. Anyway, so this is a problem where to answer different things, we broke the system up in different ways. Okay.